What's up, guys? We're looking at Advent of Code Day 12. I'm a little behind, but I'm catching up, and over the break there will be some days, I'm sure, where I can do 2 or 3. So this one is about hill climbing. It gives you a map, a very nice looking map with contours of maybe a hill or a mountain or a mesa, things that we have to go around in order to find a path. Somewhere in here there's an S on the edge, and somewhere in here there's an E over here, so we have to go from the start to the end. This is something I wanted to learn about because I know searching through, streets in Google Maps or having enemies find a way to get you in a video game has a lot of interesting thought put behind it in pathfinding algorithms, and that's something I haven't really looked into before. So this one, they give you a small test input as always, and they give you a big one like I just showed you. They are saying, okay, you can move up, down, left, or right. There's no diagonal, and from any one spot, so you've got those 4 unless one of them is too high or you're on the edge and you can't go off the map. So then you just have to find a path from the S to the E. Here's what I came up with, and it has a lot of setup. By the time you get to the actual algorithm at the end, it's really short because I knew I wouldn't be able to think of it all at once, so I did everything one step at a time. First, we read the input. The test version is here, and the big version is here, and I tried it with both. We read the input, find the height and everything, and then we rank the elevation based on they tell us A is low and Z is high, so I turned that into a number because it would be easier to work with instead of saving it till the end and converting it every time. So I made a grid with the elevation for every node, every spot, whatever you want to call it, and marked down where the start and end coordinates are. Using R and C, that's row and column. At first I did X and Y, but they don't really fit because the way you do nested lists in Python, you're really like going down to a certain row first and then going over, which is the opposite of X and Y. So then I said, okay, let's go through and find all the neighbors, because from any one particular spot, you have maybe 4 you can go to, maybe not if it's too high or if it's on the edge. And again, just like the elevation, I didn't want to find that on the fly. I wanted to lay the groundwork before we got there. So I made another grid, and this one is called neighbors. So if we say, okay, tell me the neighbors of like 5, 12, then it'll give you the ones it can move to, maybe all 4, maybe not if there's some elevation differential that you can't go up. And then the actual search is hardly anything at all. It's not much, and I started trying to do a recursive thing, but it doesn't really fit with this situation. So I ended up looking, I looked at one video, the great, as we know, Jonathan Paulson, the man, and I looked at some videos on Dijkstra's algorithm and breadth first and depth first search, and it turned out to be not recursive. This one's just a while loop. So what we do is we have a queue, which is like branching out all the possible places that are waiting to be checked, and then we have a list of places we visited, because you never want to get stuck looking back and forth between 2 spots, even though when you're here, this other one's always an option, and when you're here, this other one's always an option. You want to keep track of where you've been, because if you loop back around, that's definitely a longer way to get there than however you got there the first time. So then we say, while there's something in the queue, because we empty it out by the time we're done, we peel off 1 from the queue, and then we say, if we've visited that place, done, look at the next one. If it's the end, then I print the distance. It probably should be return, and then we put this in a function, but I knew that this was the end of the program. We would just do it. And then otherwise, we add it to the list of visited, because we're here and we're not done. And then luckily I've already done this thing of finding the neighbors, so that's it. We just look at the neighbors and check them and add 1 to the distance because we're going farther. This could be like probably done a million other ways, but this works really well, and because we did all this work beforehand, it's not too bad. So when I run this on the test data, then it says 31 is the shortest path, and if I run this on the actual data, then it says it's 400 something. Okay, so that's the answer for part 1. Now let's do part 2 together. It says, okay, instead of this, we're gonna pick any A to start from, any like sea level to start from, and we're still going to the same ending spot. Now this means we want to pick like the closest one, not closest as the crow flies because it might have a wall between them that you have to go around, but closest in the fewest steps. So obviously it would be too much to pick every A and see what the closest is to the end, because there are a lot of A's. It's by far the most common. Like if you look at this, there are a ton of A's. Actually, maybe C's also up there, but the most common. But the point is, we don't want to have all these starting points and check the whole thing every single time for all of them. We would rather just pretend like E was switched with S. Like we just say, oh, we're starting from here, and we go until we can find an A anywhere. And you don't even have to say what it is. You don't have to say the coordinates of the winner. You just have to say how many steps. So we can do the same algorithm with starting at E, going until you hit an A, and done. So let's try to do that. Actually, no, the find neighbors is gonna have to change because we can step up instead of step down now that we're going backwards. So let's say I always want to do a nice, beautiful piece of code where it's like part 1 and part 2 are labeled and everything, but for this one I'm just gonna copy paste and comment things out. So I'm gonna hit copy, get rid of that for now because we're gonna have a new version, even though most of it is the same. I could like have some nice parameter on top where you like switch one value and it does the whole thing, but let's just try it. Okay, this is going to be part 2. Let's label that, I suppose, part 1. Okay, and this is part 2. Its version of find neighbors is backwards because it used to be you could go down any amount and you could only go up 1. Now it's you can go up any amount because we're trying to find the starting point, and you can go down only 1. So I think I'm just going to switch minus to plus and switch less than to greater than. That might be off by 1, but I think it's going to be fine. So the idea of this function is just checking those 2 things I mentioned at the beginning. If you're on the edge, then we can't go off grid, so that's one thing that gets eliminated. And if you're, well, first time it was if you're running into a wall, you can't go. This time it's you can't go down because we're moving back in time. So I think that's all we need. Let's print neighbors of this version. And I'm not going to really look into the details, but if I see that it's empty or if I see that it's like some insane result that shouldn't be any good, then we'll know we got it wrong. Yeah, it looks fine. I mean, they're showing normal numbers that are parts of the grid. It's not like, you know, 4-digit integers or something. And I'm not seeing any that are negative. It looks like the kind of thing that would be the right answer, even though I'm not actually caring about looking into it and saying, oh, does this spot actually work? Actually, what we should do is use the test data again, because they say, okay, if we do this with the test data, then we get 29. So we should try that. Obviously, we're not doing that algorithm part yet. This says 7 because we're still using the old search. So now the search, we start at end. So I just have to put end in there. Those are things that I defined at the beginning. I'm going to take this off now. And then visited is still the same idea. And the movement through this while loop is still the same idea. We have our spot and distance are just things we keep track of in the queue. If we visited, we can't go there again. That's still the same. This one is, instead of saying if we've hit the end, now we go if we find an A. So I can't just use the numbers anymore. I have to like actually look it up on the grid. Grid of row call is not A, it's 0 because the grid that I'm making is numbers. So I could say 0, or I could be silly and just say not. I always love doing that, treating it as a Boolean and just saying, okay, 0 is not a real thing, it doesn't count. And then we still add it to the visited, and then we still do this exactly the same, I'm pretty sure. So let's try this. If I run this, am I going to get 29 on the test data? Well, I don't know what's going on. It didn't stop, like it kept going for 2 more for some reason, but hey, it got 29. So I'm sure there's something in here. Well, you remember a minute ago I said this should be a return. We should put it in a function so that when we hit the distance, we immediately hit return, and then who cares what would have happened afterwards. So maybe that would be a next step, but it still does find 29, and then so when we run this on the real data, we just look at the first thing, pretend the others didn't happen, and we're fine. So let's say data, and then we run it, and we scroll up because there are a lot. 451. Okay, I don't know why we got those others. There must be something to do with the queue not being empty. Like maybe I'm doing 2 of these things in the wrong order and it's not removing it before it checks. Or maybe there's something to do with the way it's looking for different possibilities than I was checking last time. I don't know. But the 451 is good. In fact, I typed that in a minute ago. And you know, a minute ago, I actually didn't have this problem, so I must be doing something very silly right now to have it keep going. But we're good. Oh, I could just say break. That's not cool, though. I would rather do the return version of this. So check to make sure it's working, at least. Yeah, okay. Let's pretend we did that and then pretend we went back later and fixed it. This was a really fun one because I like the idea of pathfinding, and I want to look into it more. Like, you know, I always hear people talk about learning the A-star algorithm and things like that, and I know what they look like on a picture, but I haven't actually implemented them. This one was really nice, and the next time I do something like this in the future, I'll want to do more of it, which is lots of setup, you know, give them numbers instead of letters, find all the neighbors beforehand, and then when you actually do the search, it's really simple. These are all short lines. There's not even any math in here because the math has already happened. It's just organizing your stuff. I know, by the way, that pop 0 in a list is probably slower than it would be if I use some other collection, you know, whatever that thing is that you can pop from both sides in Python. I'm sure that's a lot more performant, so that would be another thing to look into. But for this one, we had to add to one end and pop from the other, so I ended up having to say pop 0, even though I'm sure it's a lot less speedy than regular pop. All right, thanks for watching. Bye.